We are going to talk about the square of the correlation coefficient. Remember, the correlation coefficient itself is very useful for measuring the strength of the relationship between your y variable and your x variable. But you see, when you square it, the resulting statistic is called the coefficient of determination. We talked briefly about this earlier because it is the one that measures the percentage of variability in y that is provided by the sampled values of x. So this is very, very crucial. So the R squared of a linear model describes the amount of variation in the response variable that is explained by your x or the least squares regression line. Let's take an example to further illustrate that. We recall in our earlier example that we completed on page 13, we found a linear regression model, which was this model. So this was the regression line or the prediction line. And we're going to take that prediction line down here. So we would like to rewrite it where we have what? The travel time is 0.726 times distance traveled plus 50.6. Now, in part B of this question, we're told that the distance between Santa Barbara and Los Angeles is 103 miles. That means that you will need to travel this distance to travel between both cities. We're to use the model to estimate or predict. Take note, whenever you hear estimate, it means we're making a prediction. The time it takes for Starlight to travel between those two cities. We can use our prediction line. Bring it down and consider the case when distance traveled is 103 miles. And so 0.7626 times 103 plus 50.6, we end up with 125.378 minutes. This is our prediction. Question C, this prediction, we would like to compare it to what it actually is. If it takes the Starlight train 168 minutes to travel from Santa Barbara to LA, we have to calculate the residual and explain the meaning of this residual value. The residual, as you might recall, is the actual travel time of 168 minutes minus the predicted travel time of 125.38 minutes. And that should give about 42.622 minutes. This is a positive residual. Positive residual, whenever we have a positive residual, is an indication of under prediction. Very, very important. We discussed that because it means that the predicted value is lesser than the actual value. Okay, then question D. Suppose Amtrak is considering adding a stop to the Coast Starlight 500 miles away from LA. Would it be appropriate to use this linear model to predict travel time from Los Angeles to what? To this point. So we're looking at a case where distance traveled is 500 miles. Let's look back at the picture. Did you notice that this goes from 100, 200, 300? Looking at the gaps here, I can tell this is about close to what, 400, so 400-ish. The data points that were used to fit this linear model seem to only account only as far as what? Maybe close to 400. But the value we want to make a prediction for is for 500 miles. That is way above what? 400 miles. So in this case, data used to build the model accounts for distance ranging from 0 to no more than approximately 400 miles. What we are trying to predict exceeds that range. It is exceeding the topmost value of values used to fit the model. We do not know the behavior of the model past what, 400. So this regression model does not apply to predicting what travel time when distance is about 500 miles, because doing so would amount to extrapolation, which we're not encouraged to do because we don't know how the model behaves past what? 400. It might no longer be linear. It might now be what? Curved or any other thing else. Okay. All right. In the next example, we have a visual of the relationship between weight and height, and the scatter plot and the least square summary have been provided in this table, and it shows the relationship between weight measured in kilograms and height measured in centimeters for 507 physically active individuals. This means for each individual, data was collected on their height and data was collected on their weight. We want to look at the relationship for a bunch of them. But what we've been given here is not the raw data. What we've been given here is a computer output. How can we make use of this computer output to make sense of the relationship between weight and height? First, you have the estimates. These are your regression estimates. You have the intercept B, and you have the what? And you have the estimate of the slope. So I have that given here. If that is the case, and I'm trying to fit a linear regression model, take note that that means that my y, my predicted y, that will be the predicted weight. Then for the predicted weight, we want the slope. The slope is right here, and this is the intercept. This is the slope. So slope is 1.1017. Oh, excuse me. Let's do this way. Since I have x here, this is my x. Then whatever is beside what? Your x is your slope. So we want that to be 1.0176. And then plus b. B in this case is negative 105.0113. This is the estimate of the regression intercept. And let's see. So we have this given here. Each of these values have a meaning. Let us start with the slope. For the slope, it means that for each additional centimeter in height, so for each additional centimeter in height, how do we expect weight to respond? The model estimates or predicts that the average weight, since the slope is positive, increase or each additional one would also what? Merit an increase in the y variable. So we expect the average weight to also increase by as much as 1.0176 kilograms. Then for the intercept, that will be the value of the predicted weight when the height is equal to 0. So when the height or people who are 0 centimeters tall are expected on average to weigh about negative 0.1050113. Merely we wrote the negative, we already know that this has no practical significance because people cannot have a height, a human being cannot have a height of 0 centimeters. Okay? Then do the data provide strong evidence that an increase in height is associated with an increase in weight? This requires us, as we showed in earlier examples, to test the hypothesis regarding the population slope that it is equal to 0 versus not equal to 0. Well, we know that this shows a positive trend. So if it is not 0, then it is either greater than 0. In order to test the hypothesis, we need the p-value. The p-value for the slope is 0.000. So that is 0.000. And we're going to pull that value in here. Because the p-value is less than whatever alpha level you're choosing, 5% level of significance, as required by the question, and we can tell that this is less than, that leads us to reject the null hypothesis. So we are rejecting the null hypothesis in favor of the alternative. And the alternative is saying that the slope is significant. So that means that the sample data analyzed provides convincing evidence that an increase in height is associated with an increase in weight, probably up to a certain age. All right? Then for question E, the correlation coefficient for height and weight was given as 0.73. We have to calculate R squared and interpret it in the context of this problem. If the correlation coefficient R is 0.73, then we simply square it to get the coefficient of determination, which is 0.5329. The interpretation is that approximately 53.29% of the variability in the response variable weight can be explained by the explanatory variable height, which is the height of individuals. And that brings us to the end of this topic.